Today, we have a presentation, and we're going to talk about some of the new announcements, but in addition, we're also going to have two of our customers, Murat, Ozcan, as well as Yvette, one from Trendyol and the other one from Snapchat, tell us about their journey in building their data lake implementations as well as their data mesh architecture. So let's get started with our agenda. We'll start with talking about some of the latest announcements that we made and how powering innovative solutions using data analytics using BigQuery. I'll talk some about BigLake. Then we'll mention data as a product thinking for AI and ML at scale. Afterwards, we're going to have our guest speakers tell us about the real-world implementations. And at the end, if you have some time and if you have questions, we'll try to answer some of your questions. So for starters, it is no surprise that data volume, variety, and velocity continue to grow. But it isn't only the size of the data that is growing. Data is increasingly spread across various storage systems, different clouds. Our infrastructure and our platforms are growing to become more capable, more diverse, and more distributed across different storage systems, different regions, and even multiple clouds. One size fits all doesn't apply, and data serves an ever-growing number of use cases. BigLake powers the unification of different workloads for innovative AI and ML solutions. The different types of things that we're trying to unify here, multiple engines, for example, SQL, Spark, Python, search, remote functions, all accessing a single copy of the data that resides in multiple storage modes, be it managed storage for BigQuery, GCS, or cross-clouds through Omni, residing in multiple formats, structured, semi-structured, unstructured, bringing multiple capabilities, governance, streaming, data pipelines, and building embedded analytics, as well as integrating with LLMs and AI ML solutions. Now, when we first introduced BigQuery back in 2010, it was focused on a single use case, running SQL queries on very large data sets with high performance. Since the launch 13 years ago, we've been adding a lot of new features and functionality, and BigQuery has evolved through continuous innovation. It is now becoming at the center of our data and AI strategy. Last year, in fact, we had over 350 new innovations that were released or launched in the data analytics portfolio. It was a record number of new things that we delivered to you. And last year, we launched BigLake, which is a storage engine, essentially, for the lakehouse architecture. BigLake lets you have a common way to work with data, whether it's in BigQuery managed storage, or it's stored in open data formats, or it's in different cloud stores. This year, we announced support for Apache Iceberg, Delta, and Hudi, making these formats available for all the different capabilities that we have across the BigQuery data platform. We also announced managed tables for Iceberg. This supports a full set of BigQuery functions and features, including DML and high-speed streaming. We continue to add, or our goal is to continue to add more capabilities to BigLake and make it par in terms of capabilities with BigQuery managed storage. Governance across structured and unstructured data is critical. We have expanded our governance capabilities to go beyond data objects and to include machine learning and AI objects as well. As we become more data-oriented, the importance of data sharing grows. Data sharing allows us to share information across the organizational borders, collaborate, monetize data, and securely exchange information. Some of the new features in Analytics Hub include things like subscription management, egress controls, support for cross-cloud data sharing with BigLake as well as Omni. BigQuery Metastore, this is one of my favorite features, by the way, is a unified runtime metadata layer and an open source engine, essentially, so that you can use SQL as well as open source engines across the same set of data without making multiple copies. And this allows you to create one data object and then have your engine A access that data, and then engine B also access that same data, having access to table definitions, schema, governance, and different policies from a single unified plane of glass. If you haven't used object tables, you should definitely try them. They're really super powerful, and it shows the capabilities that you have on unstructured data. Built using BigLake, object tables essentially allow you to create tabular representations of the data that you have in storage buckets. You get full SQL-based access to all of the object metadata. You can leverage built-in machine learning models. For example, if you're using BigQuery ML to predict the likelihood of a house that's possibly being rented, you don't just need to look at how many rooms or the location or the number of bedrooms, but you can also look at the photos of the houses and make predictions on whether or not they're going to rent and how fast. BigQuery Omni is the BigQuery technology to bring analytics to your data on other cloud platforms. As much as we'd love to have all of your data on our platform, the reality is that we have multi-cloud environments, multi-cloud implementations. Omni offers cross-cloud analytics at scale through a single pane of glass. With Omni, the compute resources run local to the storage so that you have a seamless analytics experience. You run the analysis in AWS or Azure and easily transfer the result sets out of those platforms to the GCP regions for subsequent analysis. We recently launched support for Omni in new regions. We continue to add more and more regions, and we also add new capabilities on Omni. One of the things that we've added over the last year is the ability to do cross-cloud joins. It enables you to run a single query across data that might be sitting on both AWS as well as Azure. And similarly, we added cross-cloud materialized views to enable you to create a view on GCP that is kept up to date, essentially, with ongoing data changes on the different platforms. Now, as you can see, we have a lot of technology answers, but this is not just a technology problem. The technology solutions will allow you to implement the types of solutions the types of asks that are coming from your business users. But treating data as a product is critical for the success of any real-life solution. In a typical organization, we have domain-focused source teams. They understand the structures of the source data. They understand your OLTP systems and the applications. Then we have domain-focused consumer teams. They understand how to make sense out of that data, what reports to create, what are the key metrics to follow. And then in the middle, you see the domain-agnostic data machine learning engineers the IT practitioners who make the magic happen. Now, at any given point in time, there are data bottlenecks because these three groups have competing priorities that they have to address. That's why data as a product thinking for AI and ML at scale requires cross-functional data teams that are organized around different data domains. This is something that we see pretty commonly amongst our customers, increasingly so. And in a little bit, as our guest speakers are going to present their stories, you're going to see similar patterns. To enable data products, there are three fundamental tenets that we see commonly. First and foremost, it's distributed ownership. This is through federated data domain teams. They're responsible for maintaining their data. Then centralized support teams. They manage, dictate the platforms with the appropriate processes, standards, automation, and policy enforcement. And then you need to have the right incentive mechanisms that encourage an acute focus on the value of data, making it useful for everybody else. And the key building blocks for data products include domain-oriented decentralization, data as a product thinking. And when I say data as a product thinking, this is so that data is discoverable. Users can easily access, discover, and get value from their data. Automation wherever and whenever possible, along with self-serve capabilities so that the domain teams can act autonomously. Last but not least, federated governance so that we ensure access controls and policies are enforced. These data products require serverless and scalable capabilities. Some of the things that we addressed or we talked about as the new features and capabilities are centered around making sure that we have the right level of scalability, the right level of ability to scale up and down, and the serverless architectures. Separation of storage and compute, automated data management, and bringing these things together in a data-oriented thinking. With that, I'd like to introduce our first guest speaker, Murat Ozcan from Trendyol, to share their journey to data products at Trendyol. Murat.
Thank you, Sami. Thank you. Good morning, everyone. Companies who are adopting data mesh has their own style of data platform implementations. Today, I'm going to talk about our data mesh implementation and how we leverage BigQuery in this platform. I am Murat Ozcan. I am the head of data and ML experience in Trendyol, and my main responsibility is basically helping teams to build data platforms. Let's first introduce Trendyol. Trendyol is the leading e-commerce company in Turkey, operating more than 30 countries, including Europe and MENA region. We have more than 30 million downloads and 12 billion sessions in LTM. I want to introduce some of the key dates here. 2013, our first mobile app leading Trendyol to digital era. 2017, marketplace revolution, which speeded up microservice architecture transformation in the domain teams. 2021, first decacorn of Turkey. For starters, I want to give a practical guide to assess your readiness for data mesh. I narrowed down the list to 5 criteria, and I want to elaborate these criteria throughout the journey of Trendyol. Implementing data platform isn't an easy thing, and it needs resource like money and time. At the first steps or at hard times, you need someone to back you up. For us, this was our CTO, and this is sponsorship. Back then, at the start of our journey, we had thousands of tables, many data sets, many projects, and as the central data team, we were dealing with the ingesting requests and the transformation requests. And these tables, the ingested tables and the transformation tables, have many-to-many relationship, which creates a mesh, but it is not like the organized mesh. We, as data engineers, deal with data, but between us and software engineers, there are some differences in terms of disciplines. Building a data platform is actually at the end building a software development, building a software product, and you need some of the software development skills. Back at then, it's hard to say, but we don't have our centralized data team these kind of skills. So we empower our data team with software engineers who excel in this software development skills. Today, every company tries to be data-driven. I want to give my own data-driven definition for you. Data-driven is at what level your source domains are using your analytical platforms in their own software development cycles. Back then, some of our domain teams were already using BigQuery and analytical platforms in their software development independently from us. But this is not the ideal way. This was not the ideal way. Another problem for the domain teams was data schemas, schema evolutions, and data contracts. This is domain side maturity. And at the end, while you are creating your data platform, you need to have feedback cycles from the domain teams, because this is at the end developing a software product. So there should be a good level of communication. This is the data domain team maturity. This is our architecture for the data mesh platform. As Sami mentioned, we focused on two things for a successful data mesh implementation. First, we need to deliver features fast, and second, we need to create similarities for the platform users. To be able to fast delivery, you need some ready-to-use tools like services. This is exactly where we leverage and rely on BigQuery actually. As you can see, there are two layers on our platform. First layer is under the hood, where we placed all of the APIs, BigQuery APIs, Kubernetes interactions, and on top of it, we introduce mesh layer. Mesh layer is the visible layer to all of the platform users, especially data source domain users. Let me elaborate one of the APIs. For example, let's take DP Insights API. This API is crucial for creating a similarity for the domain teams, because domain teams, they already evolutioned for microservice architecture. They know very well the APIs, interacting with the APIs. So to create similarity, we introduce mesh layer and give them the APIs. When they call DP Insight API, for example, they know exactly what is happening in their data product. like number of rows modified, deleted, inserted, how many slots consumed, and so on. Actually, this API is sending the request to the BigQuery Jobs API. And we are bundling the necessary information and turn back to the user. So if we had to create these underlying APIs, it would take so much time and it would increase our time to market, which is very problematic for us. Data product quantum, you are already familiar, I think, consists of all of the code, orchestrator, infra components, cloud resource, and data contract. By this way, this data product quantum can be run in its own, can be scaled on its own, and can be monitored on its own. In Trendyol technology teams, we adopted tribe squad hierarchy. And we correspond this hierarchy to BigQuery's project dataset hierarchy, actually. Every tribe has their own project, and every squad in that tribe has their own dataset. By this analogy, we can apply global policies at the project level, and we can apply local policies in the dataset level, which can be column level restrictions, for example. By this way, we can give the source domains the ability to apply their bounded context also. We give a simple YAML, as you can see in the slides, and take the necessary but least necessary configs from domain teams. These are input and output ports, as you can imagine, schema, merge strategy, and expiration strategy. With this knowledge, source domains can create this YAML file, give to data platform, and sit back and see their ingestion start and give the permissions for anyone who wants to use the data product easily. Some specific reminders before closing the topic. We didn't expect that kind of big schema evolutions at that time when we started our journey, actually. But schema changes a lot. I mean a lot. And you need a proper strategy for versioning your data products, for example. And for the versioned data products, you can use BigQuery's muscles like wildcard tables. You need to set a policy. For us, this was the backward compatibility policy. So if any change that is not compatible with the backward compatibility, we directly version the data product. With this method, we secure the downstream data products that is dependent to the specific data product. Also, data product owners are curious about everything. You need to give the full transparency. You need to show them all of the observability, all of what is going on in the data products. And if everything goes well, this would be your first step of zero ETL process, actually. This is what is next slide. We want to create a seamless flow between the platforms. As I said, I am responsible for all of the 3 platforms, and we are trying to communicate these platforms with each other. Let me imagine a journey and try to explain throughout this journey. Let's say one Trendyol customer goes into the mobile app and makes some interactions, any interactions, click, views, impressions. This clickstream data sent directly to the Kafka servers. Starting from then, our platforms begin to work. First, domain teams who knows the data semantically ingest this data and register to the data mesh platform via self-serve data platform, SSDP. A data scientist sees that, discovers that data product, knows what is going on with the data product, with the metadata source domain team ingested, and began his analysis. After analysis, he decided to create a feature. This is where feature store comes in. With a DSL and a simple YAML file, he created his features and registered to the feature store. It is now available for anyone to retrieve and use in their ML products. He then jumps into the ML platform, which is located on GKA, on Kubeflow on GKA, and begins his experiments with extracting the data from direct the feature store. And at the end, if everything goes well, he implements and make an inference. After the inference, all the output data goes back to data mesh platform, and this journey goes again and again and again. And this is the end of the journey. I hope you enjoyed the presentation. I invite Yvette now for her presentation. Thank you.
Hi, thank you, Murat, for sharing your story of building a data mesh architecture at Trendyol. Now let me introduce myself. My name is Yvette, engineer at Snap, leading the big data infrastructure team. Today, let's talk about how we leverage BigQuery at Snap. Let's approach it from a more architectural aspect, and let's explore how we integrate BigQuery in our systems. So first, allow me to provide a high-level overview of the North Star, as well as our current understanding in our big data space. So we aim to build a unified lakehouse that prioritizes efficiency for both storage and compute. Storage-wise, we want to establish a single source of truth through the concept of single copy of data. Then, in terms of compute, we need a user-friendly ad hoc query engine. We also need our large-scale production pipelines to be efficient and reliable. And then on top of that, we also put a lot of focus on enable high developer velocity. This is to be able to enable very fast feature launches. Then where we are at today, this is how Snap is using BigQuery in a nutshell. So for storage, BigQuery is our authoritative warehouse for our analytical data. We use it to track all our user events. Then it's also one of the main data sources in our ML data pipelines. For compute, it is one of the main compute engine options in our data pipelines. Then our data scientists use BigQuery as our primary ad hoc query engines for interactive SQL analysis. Then we are also working on to enable SQL query on our BigLake Iceberg tables. Now let's look into our analytical and ML pipeline architecture in detail. Here is a high-level diagram showing our analytical pipeline architecture. So I want to highlight 3 things here. Let's go from the top. So this pipeline can be divided into 3 parts: ingestion, aggregation, consumption. So our ingestion is more centrally owned, while aggregation and consumption have a more distributed ownership. So there are a few reasons to explain this. First, we have unified data collection SDK. Second, we have more unified ingestion logic. that has a few data set specific configurations. Third, we also have very strict data quality control for our ingested data set. So for these reasons, it makes more sense for us to have a centralized team to own the ingestion pipeline so we can have strong guarantee on our SLA as well as data qualities. The second thing to note, BigQuery plays an important role in this end-to-end pipeline. It hosts our canonical ingested data set as well as the aggregated data set. It also allows the seamless integration with the downstream visualization tooling and other data processing pipelines. Third thing, at the bottom of the diagram, you can see we have various compute engines, Spark, data flow, and of course, BigQuery Compute. These are the main ones. So here is a little bit more detailed characteristics of our BigQuery usage in the analytical pipeline. Think of we're processing trillions of events daily. We have exabytes of data reads, and we run millions of queries every day. Then hosting tens of thousands of fields, as well as thousands of monthly active users, BigQuery is really at the heart of our day-to-day data operations. So one of the differential factor for BigQuery is really the UX. It requires such minimum learning curve. You basically just need a very minimum SQL skill to make it productive. So we were able to support, we were able to have an army of data scientists with very minimum engineer support. Then a few things our data scientists like about it is the discoverability. It's super easy to see where things are, the list of tables, the schema information, the partitions. And for more advanced use case, they also have the performance statistics to assist the user to do more advanced query optimizations. Then we also did our own benchmark. We found the BigQuery on native table have better runtime as well as cost efficiency for our specific metric aggregation jobs. Now let's look at BigQuery in our ML pipelines. Again, from the top, we divide this pipeline into two parts, ingestion and consumption. Then in the boxes from the left, we have various data sources, input data into our ML pipeline, BigQuery being one of them. Then data is being ingested into our offline training data storage as well as offline feature storage. Right now, it's in a hybrid mode. We have both Iceberg on GCS table as well as native BigQuery tables. Then at the right, data is being used by MLEs for ad hoc query analysis as well as downstream training data pipelines. Now you have seen we have quite a bit of storage solution as well as a bunch of compute engine options at Snap. You might be wondering, how do you decide when to use what? So we do have an evaluation framework. I like to think of as a triangle composed of three things: capability, velocity, and cost. Capability, what feature, what functionality does the platform offer? What is its scalability limit? So we don't only think about the requirements at the moment, we also need to think about what it's gonna like when the landscape evolves. Then velocity, how quickly is it for your user to be able to authorize something from 0 to 1? And how easy is it for team to productionalize it and maintain it? And lastly, cost efficiency. What is the unit cost like, such as dollar per terabytes processed? Would it meet our cost goal? So it's all about striking a balance and consider various factors such as your shape of data, your processing logic, your usage pattern, as well as user familiarity. So at Snap, even though BigQuery, as powerful as it is, it's not really a silver bullet. So for us, when the intensive ad hoc SQL query is not our primary use case, we do use other systems that interop with BigQuery's compute and storage. Some examples here, we read from and we write to BigQuery from our Spark jobs, from our data flow jobs. We also load the GCS file to BigQuery through the Airflow BigQuery operator. And lastly, we use BigLake Iceberg table, and we can query them from the BigQuery UI. So I like to close my talk with what's happening next. So right now, we are actually evaluating two fairly new BigLake BigQuery offering at Snap. One is the BigLake Metastore, and another one is the BigQuery Manage table. So the goal is really to simplify the pipeline architecture to achieve this one copy of data without sacrificing the query performance. Then we are also collaborating very closely with GCP to improve the query runtime for our BigLake Iceberg tables. There are also a bunch of items on our wish list. We like to know the access pattern of the BigQuery table by shards, because that would allow us to identify the usage pattern, identify waste, and configure the retention accordingly. And we also like to be able to use Gemini for SQL authoring. This is actually get demoed yesterday in the keynote, so we're looking forward to use that, as well as being able to see some actionable insights to use it for the query optimization. And lastly, we would like to have a BigLake Iceberg table viewer so you can see the high-level stats of your Iceberg table, such as the total number of records, total number of files, and the total file sizes.